talking about like paperwork and stuff doesn't have a lot to do with life. Anything else?
I agree. Okay, so 3.5 is limits to infinity. And what that means is down in the limit symbol, we're going to actually put an infinity symbol. Instead of limit to 2 or limit to 1 on the negative side, we're going to put limits to infinity. So the definition of a horizontal asymptote is going to help us to determine what our function does, because it either increases forever, decreases forever, or it flattens out to a horizontal asymptote. So if you can figure out if there is a horizontal asymptote, then that gives you where it flattens out to. Otherwise, it'll be going to positive or negative infinity.
Sorry for the interruption. My name is Condon. I'm going to the Media Center. Miss Condon in the Media Center. Thank you.
All right. So if the limit of x as it approaches negative infinity of f of x is some number L, and if the limit, no, that's an L, and if the limit of x as it goes to positive infinity of f of x is equal to L, then the horizontal line is y equals L. Like, for example, if the left side of our graph flattens out to 2 and the right side of our graph flattens out to 2, then y equals 2 is our horizontal asymptote. Now, there's an algebraic way to find this. There's a table way. I mean, you can always look at the graph, but looking might not be an estimate and might not be exact. But table and algebra always give you exact. So you can always look at the graph and say, oh, that looks like it's going next to the x-axis. It must be 0. But then if you can't make the math show 0, something's wrong. Now, we're going to look at the algebra way first, because that's really the way that you need to think about doing the fractional problem that you have, where you have the rational function. The rational functions are always done with algebra. And as we go through, we might discuss other problems that you might find that you maybe want to do with table. It's got to be one of those two choices for number 8 on your take-home test. All right, so first of all, we need a rule. The limit of x as it approaches infinity of a constant over a power problem. And pretty much this really doesn't matter what the constant in the power is. So that's why they're variables. And it doesn't matter if it's the positive infinity or the negative infinity. They both have the same answer. Think of it like this. If you have a power problem on the bottom of your problem, as x increases, what happens if you have like 4 over x to the third and x is increasing to infinity? Okay, the top number's not changing, the power's not changing. But let's say this is x to the third. So you got x to the 100, x to the million, x to the gazillion. What's happening to this denominator, to the whole thing? Think about it.
Getting bigger, so it'll be getting closer to 0.
That's right. As this denominator gets larger, the whole fraction is going to get closer to 0. So when you do the limit to infinity, whether it's negative infinity or positive infinity, the answer to this is going to be 0. That's an understood rule. And so because it's an understood rule, and again, I'll write it over here just to make sure everybody remembers that it doesn't matter if it's negative infinity. C over x to the r is also 0. So what you're going to try to do is do some algebra to make some pieces drop out so that the parts that don't drop out give you the horizontal asymptote. Now, as we go through this, what I'm hoping is that you will see some of the rules that we learned back in Math 3, I think, and that we touched on again last year in pre-calc. All right. Number 1. The limit of x as it approaches infinity of 4 plus 5 over x to the third. Now we're going to use calculus to do it, but I'm going to go back and show you that some problems may need some algebra done to them to make them fit the calculus. But also, I could go back and show you the algebra way we did it in pre-calc so that you can see that as well, because that sometimes can be helpful to check your answer. But I want the calculus. So, to do calculus, to do a limit to infinity, you put the limit on each one. So I'm going to put the limit of x as it approaches infinity on 4, and I'm going to put the limit of x as it approaches infinity on the 5 over x to the third. Now, if this is the limit of a constant, if a constant's a constant, does it matter what x I plug in there? No. It's still going to be 4. It don't matter if I do it to 0, 5, or negative a million. The answer at all values of that function is 4. So if I go to infinity, it's going to be 4. Does that make sense? But over here, I have a constant over a power problem. And a constant over a power problem is always 0. So the answer to this question is 4. Now, that's the calculus way of looking at it. Let's go back and let's think about what we learned in previous courses. To do this problem in previous courses, I'd have to get a common denominator and make it all one big fraction. So I'd have to put x cubed over x cubed. Does that make sense? This is not what you're going to do all the time. I just want to kind of show you this. It's a way to check your answer to make sure you did the calculus right. So if I put x cubed over x cubed plus 5 over x cubed, I get 4x to the third plus 5 over x cubed. Now, in Math 3 and pre-calc, we compared the powers. When the powers are equal, the coefficients give you the horizontal asymptote. When the powers was less than, it's always 0, and when it's greater than, it doesn't have one. So these are equal powers, and the coefficients in front are 4. So that's how we did it before. But now we're going to have to do some more complicated problems, so we're going to have to know how to do it with limits. And that's why, as we go through and do these limits, you're going to see I'm going to do some algebra that kind of is going to undo. Problems are going to be written like this. I got to get them back to this to be able to do the calculus. So we're going to actually work that process backwards a lot. So I thought it might be important to see it going forwards because you could know the answer before you started the question and then make sure you got the right answer at the end. So do you want me to repeat those 3 rules again? When the powers are equal, it's the coefficients in the front. When the power on top is less than the power on the bottom, then it is 0. When the power on the top is less than the power on the bottom, it's y equals 0. And when the power on the top is greater than the bottom, it doesn't have a horizontal asymptote. It'll be a slanting one.
So the powers on top is less
Then the power on the bottom, it's y equals 0. But if the top power is more than the bottom power, it's horizontal asymptote. It doesn't have a horizontal asymptote. It has a slanting one, which we don't have to find. Or at least I've never came across a course yet that we had to do that in high school. Okay, y'all good with those rules? So actually, our problems are going to start out looking more like what I showed you, the math over here. We're going to have to turn it back into this more simplified answer, which is not hard. It's not hard to do that, but at least you can look and see, oh, what's the answer going to be? Now let me see if I can get the calculus to show that. All right, so number 2. The limit of x, well, try that again. My board is definitely not orientated. So if I leave something off, I can't go back and add it. At the top of that too. Alright, so the limit of x as it approaches infinity, and it doesn't matter if I say infinity or negative infinity, unless I'm putting radicals in the problem. If I put radicals in the problem, that will make a difference. And I'll show you all that in a minute. Of 2x plus 1 over 3x plus 2. So if I go by my rules, all my powers equal. So the numbers in front of the x's is my answer. So when I get done, my answer should be 2/3. Everybody with me so far? All right, now we've got to figure out how to make it do that. Well, we have got to go back and try to figure out how to get this problem into simple little fractions that we can plug a 0 in for. Okay? Like a constant over a power problem. So the first thing you do is look at your problem and say, what's the highest power? Well, linear. Everybody agree? So we're going to use that linear thought to simplify this question. You're going to put the highest power variable on the bottom of each of these problems. And one of the reasons you're doing that is because somebody took the time to simplify this problem down a lot, and we're trying to unsimplify it. Does that make sense? So the only way I can unsimplify it is to go back and figure out what the common denominator was all about. Well, the common denominator for this whole problem has to be the highest power in the question. Now what happens? Well, 2x over x reduces to 2 plus 1 over x. And 3x over x reduces to 3 plus 1 over x. Oh, I'm sorry, I wrote that wrong. Thank you. That will be 2 over x. I missed my 2. Does everybody see how I did that? So now I'm supposed to put the limit on each one. And it's kind of, it's very important for AP that you show some things, and this is the rule for showing your work for limits, is the fact that you have to have the word limit on each one before you can simplify it in terms of putting like 0 in for something. So that's why you have to go through and write the limit on every term. Because once you do that, then you can use your rule that constant over a power problem is 0. So the limit of a constant is a constant. And the limit of 1 over x is 0. And the limit of 2 over x is 0 because that's a constant over a power problem. And so therefore my answer did come out 2/3 like we discussed at the beginning. Because we're using calculus instead of just learning the rules. The rules were developed from the calculus. Now we don't always do it this way. This is how we do rational functions. If I don't have a rational function, then we'll have to look at a different way to do it, because this only works because the top and the bottom is a fractional look. All right, let's look at number 3. Whoop, I wrote 4. I said 3, and I wrote 4. Ooh. All right, so our limit of x as it approaches negative infinity, we'll just do one with negative infinity this time to show that it's not any different, is 2x plus 5 over 3x squared plus 1. So the power on the top is less than the power on the bottom. Everybody agree? So my answer to my question should come out 0 if we do the math right, because that's what the power rule says. And the power rules are great, but for your take-home test you've got to show the calculus, because everything's based on calculus for the take-home test. Now if I was just doing this to be doing it, I would be using the rules because they are faster. What's the highest power in your problem? Alright, so we're going to take that x squared quadratic and we're going to put it under every term. 2x over x squared, 5 over x squared, 3x squared over x squared, plus 1 over x squared. You take the highest power in the whole question, no matter where it is, and put it underneath every term, because that would be what you would need to get a common denominator for the whole problem. And I know that doesn't really make sense because we're not even looking at this in terms of fractions, but that's what somebody did before they reduced it to this problem. So we're trying to put it back to what it was before they reduced it. Because when they flipped and multiplied, the x squares canceled out. Does that make sense to y'all, what I'm saying? If I put these two together as one fraction over x squared, and this is one fraction over x squared, and flip and multiplied, the x squares canceled out, give me the original problem. We're trying to put it back to what it was before somebody did that. So now my limit of x as it approaches negative infinity is going to be 2 over x plus 5 over x squared, 3 plus 1 over x squared, because I had to reduce all my powers down. So now we write the limit on each one so that we can show the rule and again, the only time that negative infinity affects anything is if you're working with radicals. So I think I have a radical example in my notes somewhere so I can show you how does that negative affect the question, because it does affect it when you're working with radicals because of plus or minus radicals. Remember how we had to put plus or minus on when we solve things? Well, positive and negative infinity does make a little bit of a difference on that. Alright, so we put the limit of x going to negative infinity on all of them because we want to use the rule. Because I'm not paying attention, thank you. I'm just not looking up high enough and low enough to get my numerators and denominators. I keep looking all the way to the top. Alright, so constant over a power problem always makes what? 0. So 2 over x makes 0. 5 over x squared makes 0. 3 is a constant, so it's not going to make 0. And 1 over x squared is 0, because a constant over a power problem is always 0 when the limit goes to infinity or negative infinity. So that's why this is 0 over 3 or 0. Does that make sense? Isn't 0 what we said it was going to be when we started? Because the power on the top was less than the bottom. So now with example number 4, let's see an example of what happens when the power on the top is greater. Because we've seen less than, we've seen equal to, so we should at least get the chance to see a greater than. Because that's the third rule. So we're going to do our limit to positive infinity of 2x to the third plus 5 over 3x squared plus 1. So what is the first step?
Well, if it's on top, do we still put it underneath everything?
Mm-hmm.
Under all the top end?
Right, because based on our power problem right now, we have a cube over a square, so it's greater than, so it shouldn't have a horizontal asymptote. Let's see if that's really what happens. With the power rules, you can at least know it's not going to have an answer, but that doesn't show you why. So you're right, we take the highest power cubed, we put it under each one, then we reduce them all. So the limit of x as it approaches infinity of 2 plus 5 over x to the third over 3 over x plus 1 over x to the third. Does that make sense so far? Did I write down the right stuff this time? Okay. So now we're going to put the limit on each one. Obviously, all the ones that have x in the denominator are going to be 0, right? But we got to show that work because that's part of it. So the limit of x as it approaches infinity of 2 plus the limit of x as it approaches infinity of 5 over x to the third plus over the limit of x as it approaches infinity of 3 over x plus the limit of x as it approaches infinity of 1 over x cubed. So this is 2 plus 0 over 0 plus 0. What's 2 divided by 0? Undefined. So therefore, if the limit doesn't exist, there's no horizontal asymptote. Can't exist if it's undefined. Now, that doesn't mean it doesn't have an asymptote. It just means it's not horizontal. Usually those problems will have slanting. Have y'all seen a graph that does like something like this? Where it looks like it's flattening at an angle? That's I don't know that this one looks like that, but that's kind of what they'll look like when they don't have a horizontal. It also usually only will show you one of them because one of them will be way off and you have to zoom to be able to see them both. But that's usually what they look like. All right. Now, we're going to look at a radical example. We're also going to need to look at a table example also and I don't really see a table example in my notes. So I may have to go back and turn one of these into a table example. Okay. Number 5. No, that was number 4, wasn't it? Oh, I thought maybe I numbered it wrong for a minute there. Okay, so number 5 is going to have a radical. And actually I have a couple of different examples of radicals because it depends on where they are. This example is going to have a radical in the denominator. So that problem would be done totally different than a problem that didn't have a radical in the denominator. One of the things that makes the radical so much different is the fact that you have to take the square root of the letters to see how big the power is before you know the size of the power. So on the top I have a power of 1, and if I take the square root of x squared I get a power of 1, and if I take the square root of x to the 1 I get a power of a half, so the 1 is the highest power in this problem. And a lot of times students just look at it and say, no, Ms. Johnson, 2 is. But you got to take the square root of it to know what the highest power is. So now that I know that the highest power in this problem is going to be x, the other thing is once you take the square root of this x squared, it becomes x. The powers are equal. So 2 over 1 should make the answer 2 based on the rules. We'll see if that holds true. So the limit of x as it approaches negative infinity, and we're going to come back and talk about negative infinity here in just a second, but I want to get this kind of started first. So I'm going to put x under each one. Now inside my radical, in order to put x inside the radical, I've got to think about what was it when it came out. Because to go back in, you've got to square it back. The reason for that is because if I put my problem back together, like x squared minus x, if I put x under both of these, then that's not the highest power inside the radical, because I've already square rooted it. So you got to go back and square it to put it back in a radical. So I put over x on the top because that was the highest power, but I have to square it back to put it back in the radical. So that's a little tricky thing. Then the other thing that I think you might want to know about radicals is what happens if you have negative infinity versus positive infinity. It doesn't affect anything but radicals, and it affects radicals because of the plus-minus situation. That sometimes the radical has a plus in front of it, sometimes it has a minus. When you're doing negative infinity, you have to put a negative in front of that radical, because you're going in a negative direction. So that's where the plus minus thought comes into play, because if it was positive infinity, I wouldn't have put it. But because it's negative infinity, the radical gets a negative. Everybody with me so far? Okay, so now we can do a bunch of reducing. The limit of x as it approaches negative infinity of 2 plus 1 over x over the square root of 1 minus 1 over x. Now, as you put the limit on each one, you put it on the inside of the radical, which is, I didn't mean to drop that negative, which is why this negative on the outside is so important, because when you put your limit, you have to be inside the radical. So the limit of x as it approaches negative infinity of 2 plus the limit of x as it approaches negative infinity of 1 over x. And actually, I did leave out a step in here. Technically, we should have put the whole thing over x and the whole thing over x squared and then separate it, but I'm letting that go. I think we can think that out without doing that. 1 minus the limit of x as it approaches negative infinity of 1 over x. So there we go. So that's how you put all your limits in when you have a radical. You have to put them on the inside because the items are on the inside.
So it's subtraction at time?
It was originally, wasn't it?
Okay. I get that.
So we get a 2. The limit of the second one is 0. We have a negative on our radical. The limit of this one's 1. The limit of that one is 0. So we get 2. Square root of 1 is 1 times the negative is negative 1. And it came out negative 2. So now let's go back to here. So the square root of this would have come out to be x. 2x over x comes out to 2. The negative came from the fact that we were going to negative infinity. Does that make sense?
Yeah.
So we wouldn't have got that negative if we hadn't put it into the question with the power rule. Does that make sense? Now, we have one other radical thought. It's not a fractional problem, but it needs to be done a certain way because it has a radical in the problem. And it deals with conjugates. So in number 6, we're doing the limit of x as it approaches, I think this one is also negative infinity, but I don't know that that matters, so I'm going to put positive infinity just for good measure. If you remember, conjugates are adding and subtracting problems that look like half a food line. Does that make sense? So in this case, I don't see any fractions whatsoever. But I can't work a problem that has a radical where it's at. So first, the first thing you do is you work out food line on top and bottom so that it will simplify this question some. It's something we do a lot to do limits, but you may have forgotten about that. So does that remind you of food line now? So we've got to put these two together on the top using the food line rule about first times first and last times last. So first times first is x times x. So that's going to be x squared minus, because negative times a positive is a negative. Radical times radical does what? Cancels, but then it puts parentheses in because you took it out of a grouping symbol. It's still got to be in some kind of grouping symbol. The bottom 1 times anything stays the same. So if I distribute the negative, do you see that the squares cancel? Does everybody see that? Okay. So if you distribute your negative, that's going to be negative x squared, negative 3, so I'm just going to have negative 3 over my denominator. Now, this is a number over an expression, so we might need to think about what does this expression do as I put bigger and bigger numbers in. So as I put, might have been easier to do this with negative infinity. If I put a positive number here and square it, the bigger that positive number gets, the bigger the square root answer is, right? And then if I take that square root answer away from the positive original number, then I'm still going to probably have a positive number most of the time, I think. But I might not be. It might sometimes be negative. I don't know if I can use the rule for that one. Okay, so we got it this far with algebra. Let's take a look at a table thought, see if it's going to come out right. To do a table thought, when you do tables like this, you know how we used to put the number in the middle, we did 3 numbers on each side with 0s and 9s? Well, this table thought's not like this. This is table of thought to infinity. So you're doing, and it doesn't really matter what numbers you use, but I use base 10 because I think it's easier. So you do 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and so on. And usually by the time you get to 10 to the 3rd, you might can tell what it's doing, and if you can't, then you might want to go more, like 10 to the 4th and so on. So we would put this formula if we can't do the algebra when we get it down to the end. And sometimes you can't and sometimes you can. If the problem had been all multiplication, we could have used our power rules and kept working on it. But since it's not all multiplication, we're just going to look at the table thought. So you put this into y equals, and you go to that value button, and you put in these numbers to the value. But now 10 to the 0 is 0. That's 1. 1 minus the square root of 4, which is 2. 1 minus 2 is negative 1. And negative 1 of that would be positive 3. I can do that one in my head. Now the rest of them I can't, because they're not going to be nice numbers. But the one with the 0 power usually is going to be a fairly nice number. So we're wanting to see what happens as we put in 10, 10 squared, 10 to the 3rd, 10 to the 4th. And if you'd rather type in 100, 1,000, 10,000, you can do that too.
So whenever we're doing this with the problems that goes with the 10-step thing, we use
You either do algebra and the power rules work, but if you get to the end and you can't use your power rules, because see, I can't do power rules on this one. Well, I don't think I can. We'll go back and let's figure out what the answer is, and then we'll go back and we'll look and see if we can use a power rule. Where we were doing the rule on, well, not just that, but where we were putting like x under all of them or x squared under all of them. Well, yeah, but I think we might can, but I'd like to see what the answer is to make sure that it's going to do what we think it's going to do, because I don't have any work on my paper, so I don't know how I did it. I guess I ran out of room and just didn't write all the work down. So I'd like to know what the answer is going to be before we try more math. So when you put this in, what's 10 to the 1st going to give you? Now we're using the value button under calculate. I don't know which calculator you're on. Really? 20? Huh. Well, that sure ain't doing what I thought it was going to do. Okay. 20 point something. What's squared? 10 squared. Did you put parentheses around the whole bottom?
Yes.
Okay. Just thought maybe it might not be doing the math right. That's not what I thought it was going to do. Is it 20 positive or negative?
Positive, but it won't let me do so.
Why? What's it giving you?
See, error. Says invalid.
Well, it can't be invalid.
Not 200.01.
Okay. All right. Well, that might be making sense. All right. What did you say you got again?
200.0.
All right. What do you get for 10 to the third? Mm-hmm.
I can't, it won't let me do it with the like, putting the exponent. I have to do like 1,000 instead. It's not, I don't know why I'm doing that. 2,000.
That's what I was thinking. It's got a pattern to it. Well, wait a minute. You can't put the square in there. If, well, maybe you can. Yeah, I guess you can. Okay. All right, so the next one's probably 20,000. All right, that's not the answer I thought it was going to come out to be. So I'm going to keep trying to go with the other one.
I won't do like anything. It didn't do the first one.
All right.
You think it's cost us? I don't know if there's doubt.
All right, so as you can see, if it goes from 3 to 20 to 200 to 2,000 to 20,000, I left a zero off. It's going off to positive infinity. As this goes to x goes to positive infinity, the whole problem's going to positive infinity because your graph's going uphill. Well, let's see if we can make the math do that. The limit of x as it approaches infinity. Now remember, you take the square root of the inside, that's x. The highest power in this problem is x. Does that make sense? So if I put negative 3 over x over x squared over x squared plus 3 over x squared, because remember, when you put it back in the radical, you got to square it back. That'll give me the limit of x as it approaches infinity of negative 3 over x. Let's put the limit on as we reduce to save a step, y'all. X over x becomes 1, so we're going to put the limit as it goes to 1. We're going to do the limit of x as it approaches infinity of 1 plus the limit of x as it approaches infinity of 3 over x squared, all inside that radical. So, what's negative 3 over x answer for infinity? Constant over power? 0. Alright, I got 1 plus the square root of 1, which is 1, plus 0 for the other one, right? 1 plus 0 is 0, so that's coming out to be 2. The algebra says it should be 0, which is the answer I have on my paper. So my question is, why is the table not showing that? Go back and type the original problem in the calculator. Y equals the original problem before we started putting stuff on it. Okay. Is it going off to positive infinity?
Yep.
On the positive side? What's this negative side going to?
It's just,
So I say, y'all might need to zoom out. We might not be able to see what it's really doing. You know, it may be that it gets out there to 10 to the 10th power, starts going back down or something. You know what I mean?
You wanted to see the original graph?
Yeah, the original graph. Always graph your original if you have a conflict between doing a table and doing your algebra, or a rule and doing algebra. All right, since we're having a little bit of conflict in the answer, well, let's look at the negative side of the chart. So if you do 10 to the 0 power, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. Wait a minute, I did that wrong. I put the negative in the wrong place. Negative 10 to the 1, negative 10 to the 2, negative 10 to the 3, negative 10 to the 4 is what I meant to say. The negative 10's in front of the power problem.
on the 0 too.
No, the 10 to the 0 power wouldn't matter, but we can throw it in there.
Yeah, that's right.
Because it's 1 or negative 1 won't make any difference. But yeah, we could put that in there. I'm just curious on, does it show that answer?
You want us to get the value thing on the original?
It don't matter. Sometimes doing the left and doing the right don't give you the same answer if you don't deal with that negative situation. So I'm wondering if that's what it is. Because it's showing the answer on your graph for negative infinity. And the algebra is showing negative infinity's answer. I don't know why it's not showing the positive infinity's answer. So I'm trying to think about what could have caused that. Because I changed this problem from negative infinity to positive infinity when I wrote it down. Because I didn't want another negative one in a row. Maybe I should have left it. But then that makes me wonder why would the positive infinity will not work algebraically. Alright, are they getting smaller? Like closer to 0? But if you put it in there and square it, it should come out positive. You gotta have parentheses around your number, by the way.
I went from 0.15 to 0.015.
Okay.
And I'm still trying to zoom out.
So 0.5 to 0.05?
0.15 to 0.0.
Okay. Was 0.15 this one? Or this one?
No.
This one? Alright, so negative 0.15, negative 0.05. Is that what you're saying? Okay.
0.015.
15. Oh. 0.0. Like that?
10 to the second be the same as the negative 10 to the second?
Because you got that negative in front of here that's affecting the answer. Because I put a positive number here and a negative changes how the adding and subtracting is done. Okay, well that looks like that's getting smaller, and that does fit the 0 thing. Absolutely, doesn't it?
Why wouldn't negative 1 and 1 not make a difference though?
Yeah, it makes a big difference when you put it in front and there's no way to get rid of that negative.
The 10 to the third is 0.0015.
Okay, so it is getting smaller. So then the limit of negative infinity is 0. The math we did, so let's go back and let's put a negative on every one of those infinities. okay? Because that fits the math. Not sure why it doesn't fit the positive one. I'm not sure at all. I'll have to go back and investigate that because normally they give you the same answer.
Oh, wait a second. What am I saying?
No, you didn't.
I think I told you. It's still getting smaller, but I think
It's getting smaller.
wrong.
Well, it's still getting smaller. I know that part's right. So it makes me wonder, how would we get the positive answer correct? So I'll go back and I'll investigate this a little bit. Because I would have thought positive infinity would have worked, but that radical's doing something to it. So I got to go back and think, how's that a radical affecting it? Because it's doing something, because it's not giving us these answers.
Would it be like a positive on it, if a negative on it, would it change the sign?
I don't know that we can do that for this question because we're using conjugates, but I'll have to think that through because what this is showing me is the problem should be undefined, and for the problem to be undefined, I would have to get 0 on the bottom, and I'm not getting 0 on the bottom.
Storm south, is it? Oh, I see what you're saying.
See, so it works for the negative side, but it doesn't work for the positive side. That makes me wonder. Not that they both have to have the same answer, by the way. They don't. Let me see. No, because you put the parentheses between the square and the 10. You put it on the outside. It's got to be between the 10 and the square. All right. So this one's a little strange. 9 times out of 10, if you do the positive and you do the negative side, they come out the same answer. Let me go back here for a second. When your problem is a rational function like this, it's already in a fractional form. The left and the right usually have the same answer if it has a horizontal asymptote. But some problems only flatten out to a horizontal on one side, like exponentials. They only flatten out to one side. So that means that when you're doing those problems, your tables won't match. And the algebra will only work for one side or the other. It doesn't work for both because it doesn't have a way of showing both on every question. All right. Now, our next question is kind of an interesting question. They don't want you to use the algebra and they don't want you to use the table. We're going to use something that we haven't really talked a lot about this year, but we're going to focus on that for a few minutes with this question. In number 7, they want us to look at a trig answer. So that's why there's not going to be an algebra way to do this one with thinking out I can't put X under everything and do that kind of math when it's trig. And I don't think in this particular case it matters whether I'm going to infinity or negative infinity for the math I'm about to show you. So when you've got something you can't do algebra to, but you really would like to do something besides a table method, which table's a great method for it, but sometimes tables don't work very well. So we can do what's called the squeeze theorem. I misspelled that. I can tell that already. There we go. Squeeze theorem. The squeeze theorem allows you to graphically figure out the answer. Not table, not algebra, but graphically. And what it does is it gets rid of the complicated part of the question and gives you a much simplified graph to look at. And so let me explain. What complicates this problem is sine of 2x. If that wasn't up there, I'd be able to figure out the answer a whole lot easier. Does that make sense so far? So what they say is take out the complicated part of the problem and just put a 1 in its place. And compare your graph. Well, we don't know in some respects whether we want to look at this from a positive or negative scenario. So I'm going to take out sine of 2x and I'm going to put negative 1 on top. And I'm going to put positive 1 on top because I want to focus on the fact that x is on the bottom. But I also want to focus on the fact that I took out something that was much more complicated and put in something real simple for it. And you always put a positive and a negative. And you turn this into a between. Well, that 2x looks really bad. So what you're going to try to do is squeeze the sine function in between these two more simplified functions to see where they go. And you actually graph all three of them. But what you want to focus on when you graph all three of them is what do these two squeeze this into as you go to infinity. Okay? So I would suggest bolding this one or knowing what color it is if you have a color calculator. Because knowing what color that's going to be graphed in, you want to be able to see it and see what the two on each side of it are doing. So I have to bold because I don't have color. So if I go to y equals, and let's see here, come on. Take out what I got in here. I'm going to put in the first line negative 1 over x. And, well, it would be nice if I'd have got the x before I moved down. I'm going to click on the computer. It is not orientated well enough for me to do anything up there. And I'm going to put 1 over x in the second line. And I'm going to put the original problem, sine of 2x over x in the third one. And I'm going to bold the third one. Now, I don't know. Y'all that have the color, you can tell what color it is. But I'm going to bold it by clicking enter on the third y equals over here. I want the one that was in the middle bolded. Now, you can put them in straight order if you want to, but I want to focus on the one that graphs last. So that's why I put it last, to see where is it with the other two. You with me?
I mean, it was something great.
All right, you got to be in Zoom 6 to get started, but that doesn't mean you have to stay there.
You gotta like,
Right, if you do Zoom Fit, it might do better. So I'm going to do Zoom Fit next. I always start with Zoom 6 because Zoom 6 is kind of one of those things you just got to kind of get yourself started. All right. So as you can see, my boulder one went right through the middle, didn't it?
mine goes like,
Oh, wait a minute. I might have degrees turned on. Hold on. I do. Yeah, I got degrees turned on. Let me go back and turn on radians.
mine's like a little pretty picture.
Yeah, there's your squiggle. All right, so what's it doing? Well, in the middle there's something great going on, but as it goes closer to the end, as I go to positive infinity, what's it doing? Well, if you're not sure, sometimes you can do what's called zoom box. So I'm going to do zoom box number 1. I'm going to come down and come over closer to the other side so I can box in what it is past this loop here. Y'all know how to do zoom box? Zoom box, you first hit zoom box and this little cursor comes up and you go put your cursor where you want the corner of your box to start. So I want it to start down here so that I can go over and up. So you hit enter once and you draw your box over as far as you want it and up as far as you want it. And then it takes just what's inside that box and blows it up. Does that make sense so far? So I hit enter, and it'll show me the 3 pieces of the line that I'm wanting to look at. What you'll notice is it squeezes my curve between these two. Does everybody see that? Now, if I go over more, what are these two curves doing as they get closer and closer to a positive infinity? they're squeezing it more and more. And what's it going to eventually go to? Okay. Think this. No, that's not. I mean, what number? Right, it's going to squeeze into 0 because see how it's getting closer and closer to the x-axis? It's going to squeeze that curve in smaller and smaller and smaller till eventually that curve will be on 0. I'd have to go way out to be able to see that, but it really will do that because these two are coming in closer and closer to 0 because 1 over x has a horizontal asymptote of 0. So, my answer to this question, 0. So that's one way you can do some math sometimes when you have something more complicated, doesn't look easy to work with.
Well, all trig we have to use that.
No, not necessarily. Not all trig uses that. So that's and I could have made a table to see that as well, y'all, because we could have done the 10 to the first, 10 to the second. I just wanted y'all to see the graphic view, because I think sometimes the graphic view can clear up some mysteries with it. Now, I have one more problem that I definitely want to do today, and this problem, it's going to be algebra, but it's going to be a little different. So with question number 8, I have the limit of x as it approaches infinity of x sine of 1 over x. I have a problem. Not all my x's are inside my sine this time, and the fraction is. So I can't do the squeeze theorem because I can't take the sine out because it's not in the fraction. It has the fraction inside of it. Does that make sense? The reason I could take sine of 2x out in the last question is because it was all in one numerator or one denominator. But I can't do it when the fraction's inside the trig. So there's another thought that relates this. And that is, what if you take what you have here and substitute something else in for it? And so the substitution method works fairly well. It's a little different algebra method. With the substitution method, you take what is inside of your sine and set it equal to t. So you say, I don't want 1 over x in there, I just want t. And we'll talk about that x on the outside in a second. But does everybody see how if I put that t in there, that looks a lot more simplified than 1 over x? But the problem is I have an x on the outside, so if I'm going to change this to t, then I'm going to have to change the whole problem to t. Okay, so right, we can solve this by switching the diagonal. Whoop, let me lay my eraser down. Switching the diagonal. Help if I could write an equal to mark and make it 1 over t. Because you can switch your diagonal and solve for x. So now this is going to be 1 over t. Now this x out here is going to have to change because in this particular problem we have changed what the infinity is going to be about. I'll come back and talk about that in a minute. But couldn't I simplify this a little bit and say this is sine of t over t? Couldn't I multiply 1 over t times that and put it all in one fraction? All right. Now let's talk about how we're going to change this. Well, I don't mean to put an equal mark. I meant to put an arrow. So now, since it's all about t, we've got to figure out what's t going to. So you go back and look at the formula you substituted in and think about, as x goes to infinity, what does 1 over infinity do? As you go to infinity down here, what does it make the fraction do? Is that go to 0. And so therefore, since it's going to go to 0, we can change this to 0. So you have to think about what your substitution did to get your new variable. Now, since this is positive infinity, we're probably talking about the positive side of 0. If I was doing negative infinity, I'd probably be doing the negative side of 0. Now, does anybody remember this trig from chapter 1 at the beginning of the school year? What does sine of t over t represent when it goes to 0?
Oh, it's 1 or 0.
It's one of those two.
I just can't remember which one it is. I think that one's 1. No,
That's- It's 1. The one about 1 minus cosine of x over x is 0. So when you're doing a limit to 0 and you have that function, it's an automatic known answer. And that's why you want to do the substitution, because you can get there with it. Now, I have one question that I skipped I think I want to go back to that's really short. I have some other stuff written here, but I don't think I necessarily need all of this to be able to do what y'all need to do for number 8. I've shown some things for that, so I'm going to do one more and we'll be done. Number 9. The limit of x as it approaches infinity of 1 over 2x plus sine of x.
When do these limits, like, for the 10-step problems, we use the original problem that you gave us?
And we're going to go back and talk about that just a little bit here in a minute, to clarify step number 8 for you. All right, so in this problem, I got some issues here because I can't put x under all of them. Well, maybe I can. I don't know. Because if I put x up there, that'll be 0, right? If I put x here, it'll be 2, and if I put x here, it'll be... Well, maybe I could try that. I didn't write the workout for this one. That might work. We'll try it. So if I put x under each one, because x is the highest power, right? That would be 0, that would be 2, but we don't know what that is. Does everybody see the problem? Because this isn't 0. See, sine of x over x isn't going to be 1 unless your limit is going to 0.
because it's only 1.
Right. But we still might can figure it out, so we'll see. So we got the limit of x as it approaches infinity of 1 over x that we definitely know is 0. Everybody agree? All right. And we have the limit of x as it approaches infinity of 2, which we know is 2. Everybody agree? And then we have the limit of x as it approaches infinity of sine of x over x. And that's the part we're not sure about. Well, no matter what number you put in there, sine of any number is going to either be positive or negative or 0, right? If you go around the unit circle, they're all positive, negative, 0. Everybody with me? And that means that the biggest number I could have is 1 or negative 1. You with me there? So if I go 2 plus negative 1 over whatever number, or 2 plus positive 1 over whatever number, that would be my biggest answers I possibly could get. So this is a fraction. When you go to positive infinity, you don't get a 0 on the bottom, right? You're getting a bigger number every time to divide by. But this number on the top is all the numbers between negative 1 and 1. It's the most it can ever be. So the bottom is always going to be pretty much bigger than the top. Because if you put in anything, when you get way out towards infinity, it's going to definitely be bigger than 2 pi. And 2 pi is 6 something. Does that make sense? So if I have a negative 1 to a positive 1 type numbers, divided by this, that's just going to be some kind of positive or negative number. Don't know what the number is, but I know it's going to be positive or negative number. Added to 2 is still going to be a positive or negative number. It's not going to be 0, is it? Everybody agree? Then the answer is 0, because anything divided by 0 is 0. So you can reason that out by just knowing that this is going to get larger, making your fraction smaller, but the top is always going to be between -1 and +1. So it's not going to get bigger. All right. Now, let's talk about your problems here for a minute. Let me see if I can find that document and bring it up so we can,
Which problems?
so that way she can see it in the video. Your take-home test. No, wrong one.
We have some notes we never finished either. That's like the, what is it, 7 through 8 or something?
7 through 8. Okay.
Part of the study guide.
Oh, yeah, we can't do that quite yet. We might do that tomorrow. Okay. I don't see them all in one file, so I guess I'll just open them up individually. Oh, wait a minute. No, this might be it. Yep, this is it. Okay. So, I don't know if you want to write this down on your, I guess you could write it on the set of problems. To like write something next to the word polynomial or rational or whatever. So polynomials are fractions already, right? And they don't have radicals in them either. So you probably should do a table method on this one. And in your table method, you'll want to do a table for the positive and the negative side. Does that make sense? Like you'll do 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, figure out what that's doing to positive infinity. Then make another table for the limit of x as it goes to negative infinity. To show your work for that, I mean, the table is the work, but to show your notation, you would say like the limit of x as it goes to positive infinity of f of x. I know these aren't written in f of x format, well, we'll use that anyway. And then you'll make your, whew, that was weird. And then you'll make your table and say 10 to the 0, 10 to the 1, 10 to the 2, and so on, till you figure out how many you need. Keep adding to it till you figure out what it does. Then do the limit of x as it approaches negative infinity of f of x, and make your table. And 10 to the 0 is on this end with negative. Negative 10 to the 1, negative 10 to the 2, and so on. And you'll write your answer up here next to f of x equals. Does that make sense? We good on that? We understand what I'm saying? You're going to do a table for polynomial. Now for rational, you're going to do the x stuff with algebra. You're going to put, the powers, pick your highest power, put it under all of them, do the math. Because that's what rationals do. And then with the fractional one, do a table. And I think trig will be a table also.
Tables of polynomial.
Uh-huh, like you did for the polynomial. And I guess the absolute value is going to have to be a table too, because I don't think you can do algebra to any of those. The only ones I know you can do algebra to are the fractional ones, the rational ones. Okay?
I had a specific question about my absolute value problem.
Yeah.
The way you just had to do it like the derivative of that,
Uh-huh.
I didn't understand how to do it because I have like a number that's added to outside of the absolute value thing. How do you put that in there if it's like,
Isn't it? I don't know, look. Let me assign this homework real quick so I can get this video started. So our next quiz that we're going to take is going to be tomorrow. And before we take that quiz, we're going to check the homework and we're going to try and finish that study guide because it's going to be a really short quiz. So your assignment for this is, okay. This is page 193. Page 193. I want you to do 2 through 10 even. The first 3 of those you're matching a graph. The second 2 you're doing a table. And then I think I'm going to assign y'all 12, 20, and 26, and 30. And those is there's probably something of each one of these that's kind of, one is the fractional algebra way, one's the radical thing where you got to remember to put the x square inside, one is substitution, and one's conjugate. So you got one of each kind. I didn't give you a squeeze though. Is there a squeeze one in here? I don't see a squeeze one. So that gives you one of each algebra way to try. 2 through 10 even is look at the graph and make a table. 3 of them are graph, 2 of them are table. 12, you're going to do math based on the highest power. You're going to put the highest power under all of them and do algebra. 20, you're going to do the same thing, but there's a radical on the bottom. 26, you're going to do substitution. And on 30, you're going to do conjugates. Does that make sense? And if you forget what that means, this video will be out there for y'all to go back and listen to the last few minutes if you forget what you're supposed to do. Because I'm going to post it for her out on Canvas. Now, let me...
And then